Hello, this is Chris Kenberg, and I'm presenting part two of topic one, which concerns scheduling. And in particular, the examples that we're going to look at are lists and disks. So here we go. It complements the face-to-face version I gave on Thursday last week, and it actually duplicates the session I gave online on Friday. Okay, so here we go. Um, the video that we've just actually looked at asks you to imagine an aircraft flying 1 millimeter above the Earth's surface and circling the Earth every 25 seconds, possibly examining each blade of grass. And this model, this idea, indicates roughly how a disk drive operates. Gives you an idea of the performance of that disk. Okay, we're about to introduce scheduling and consider some algorithms for performing scheduling. And all I mean by algorithm here is informally uh, a set of steps that will actually achieve our given purpose for a particular task. In the case of hard disk scheduling, uh, there's a problem which I'm going to identify, and a schedule for the uh, hard disk read or write head is going to enable us to read or write data that's been placed on the hard disk magnetically with an extreme degree of accuracy. But in any case, let me say a little bit more about scheduling. Um, a schedule is important in all walks of life that I can think of, and you might find it a bit daft to give you the following example, but the example is um, you having dinner with a plate of food in front of you, and maybe the plate of food contains a portion of peas, a portion of potato, some gravy, and maybe some other burger, whether it's vegetable or animal. I'm not interested. Now, to eat it successfully, eat your meal successfully, assuming that it's quite appetizing, you've got to schedule the movement of your fork and knife in a particular sequence of steps, enabling you to perhaps eat a portion of the peas first, and then a portion of potato, and then maybe you tuck into the burger a little bit, and then you go back to the peas and so on. Another example is you've built a mechatronic device like a robot, and you need to program it to schedule itself to leave the room that it's in at the current time. And that might involve getting up from its seat, turning round, orientating itself towards one of the three doors in the room, opening the door without colliding with any intervening furniture or pushing people over, and then navigating itself out of the building. I mean, maybe it's Mandeville Place, it's the building that we're currently in at the moment. And then it's got to either take the stairs downwards, or take the lift, or take the second staircase. And the schedule actually is going to depend on perhaps what the robot wants to achieve. I mean, does it want to leave the building at the earliest opportunity, or maybe it needs to stop on the floor too for the purpose of charging its power cells? Third example, and these are completely random, is that you want to cross the road outside the building, and it's actually very busy, and the traffic's moving at quite a high speed in both directions. How are you going to do it? Well, you've got to walk to the edge of the pavement and then stop, and then possibly you're going to choose a particular time when no car is moving from the right to the left, which would in principle allow you to walk safely to the middle of the road and then perhaps stop and then perform another feat of scheduling to get yourself to the opposite side of the road. So maybe you're waiting for a gap in the traffic, waiting until it's safe, and then you're moving at a particular speed. If you've got a narrow gap, maybe the robot's actually going to run at high speed. And you can imagine the possibilities. So even, what, I've forgotten whether it was you or the robot having to perform a schedule um, to get across the road. But in either case, logically, somewhere in the background, there is going to be a schedule. In other words, a sequence of actions which, when taken in a proper sequence, is going to achieve you obtaining the particular outcome, the particular task. And again, I can think of a slightly more interesting case when you're talking about a BMW's collision avoidance system, and it's constantly scanning what is in front of you, and it's taking measurements of uh, the distance between your car and the object in front of you. And there's a threshold which uh, the the control system is going to decide that, well, you're getting a bit close, so slow down. Or perhaps the 4x4 in front of you slams on its brakes, and you, the BMW driver, is at risk of slamming into the back of that 4x4. So some kind of emergency avoidance technique is needed to obviate an accident, and then maybe it's swerving to the left because you're travelling at high speed. So please think about different examples of schedules, and um, uh, as I said, a quick working definition is a particular objective with a sequence of actions or operations that will enable you to realize that particular objective. Think of it. Think of it. Maybe it's very down to earth. It's like you having to get the back garden dug and cultivated. How are you going to do it? What's the best way of doing it? What's the easiest way? What's the most effective way of doing it? Anyway, let me know of some examples that you've come up with. So today's object of interest is this picture, this obviously mechanical-like device, and I can identify something like an arm positioned two-thirds of the way across this silver-looking plate. This is called a hard disk platter, and there's a spindle here, like an axle, around which this disk revolves. And giving away a little secret, well, the arm can actually be positioned here at the outside edge of the plate, or it can be moved at very high speed right towards the centre of the hard disk drive. And here you've got a box of electronics, and mainly the electronics are going to control the movement of the arm and the actual movement of the disk. So the disk, let me tell you here, is moving very rapidly. I mean, remember the analogy that we started off with was some kind of vehicle that's almost floating above the Earth's surface at a few millimeters, and it's traveling round the Earth's circumference once every 25 seconds. And hopefully you can, just Google the question, what is the Earth's circumference? And I reckon, if my memory serves me right, something like if you're measuring the circumference connecting the two poles, it's around about 40,000 kilometers. So perhaps I'm asking you to imagine a device that is actually performing a lot of work every time it goes around the Earth, like maybe measuring the size of each blade of grass, or maybe photographing it, or something along those lines, on its journey, on its high-speed journey. And we know it takes, as I said, it takes 25 seconds just to go around the Earth. So you could actually calculate the velocity in kilometers per second. Could you do that? Just give me a rough guide. It gives me an idea. And the second question I'm going to ask you is, well, take a typical hard disk drive in 2020. How fast does the platter revolve? How fast does it revolve? And secondly, how quickly can this arm move position? Well, I'm going to make the question a bit more precise in a few minutes. Have a look at this reference. You get a bit more information, and I think it's quite a good reference, online reference, secondary reference to getting more information about hard disk drives. So have a look at that. So the first thing I want to draw your attention to is that given a hard disk platter, typically you're going to have up to or more than, it depends what hard disk drive you're looking at, 300,000 different tracks. So a track is a very narrow concentric circle representing an area of magnetizable material onto which there has been onto which can be written ones and zeros representing different bits of information. Or a track can actually store, well, if it stores ones and zeros serially on each track, those ones and zeros can be read by means of the disk driver's read-write head. So the idea of a track is that it's simply a concentric circle, one of possibly 300,000 plus such tracks. Okay, the writing device looks a bit like this. I mean, this is the real functional part. It's this shape. It's this shape. And using this device, I can manage to write a logic 1 or a logic 0 onto the disk's surface. And I'd really appreciate it if you can actually tell me a little bit more about the writing device. Like, what's it made of? What are the principle of its operation? I mean, have a go. I'm not asking you to anything degree level. It's just a bit of basic information about writing heads, the hardware needed to write data to a hard disk. Okay, so the write device that I've just shown you moves over the track. moves over the track. Here it is. Do you recognise this shape? Okay, and this is the track. And to me, the very interesting thing is that the width of a track is around 84 nanometers. So hopefully, that gives you a clear idea of the smallness of the width. A nanometer, a millionth of a meter. Is that right? So a second interesting thing is that um, to gather, no, sorry, to write data onto the disk, the write head, so it's this hardware device, is going to float approximately 5 nanometers above the platter. And in case you didn't know, 5 nanometers is roughly the width of 2 strands of DNA. Very, very small. Can only be seen with a powerful microscope. And, what have I got here? It's just another illustration. Here's an example of a right head that's actually following, is aligned to, is synchronizing its position with a particular track on the hard disk. One of 300,000 maybe. So the read device, which is magnifying this representation of being able to sense the difference between north and south poles, two different poles, used to represent magnetic poles representing a 1 or a 0. It's been magnified 85,000 times. Tiny. And when I first read up about all this, I just thought, goodness, this is a real brilliant engineering accomplishment to build devices that can reliably work at such a small scale. Anyway, putting read devices together, I think I've got 3 of them here, so I could, in principle, read 3 platters. I've got some electronics here, and the actual electronic read head is in this vicinity here. So that's what it looks like, and it's packed with micro electronic circuits here. And here it is again. And the scale of this device is that this distance represents 1 millimeter. So the read head is going to be somewhere in this area, and packed with electronics, and the data flows out after it's been identified whether the data is a 1 or a 0. So the overall structure of a hard disk drive, excluding the read heads or the write heads, is that I've got a disk platter here, and these 3 items, which I've drawn in green, represent 3 different tracks, 3 of 300,000. And what I've marked here is just a little section of the first track I'm talking about. And this track contains a fixed number of bytes. Remember, a byte is just 8 bits, fixed number of bytes. It could be as many as 4,096 bytes. And all the sectors on the disk are of uniform size, and each of these tracks are split up into sectors. And just by looking at the diagram, you should be able to, you will realise straight away that this inner track contains fewer sectors than this middle track, which contains less sectors than this track, which is close to the boundary of the platter, the outside boundary of that tractor. So this central object is called the shaft, and it's the means by which each of these four platters are revolved at high speed. And a little bit of further technology, further bits of terminology is that if you imagine this particular track, supposing it's track number 4000, then look at track 4000 on disk platter number 2, and look at track number 4000 on disk platter number 3, and on 4. And you can imagine that these tracks are going to form logically a virtual cylinder. It's not a real cylinder because there's a big space between each track, but together you can refer to the cylinder. Okay, so the diagram I'm showing you now represents the situation that I want to examine and for the next few moments. Here I've got a representation of the read or write head, and it's capable of moving from the edge of the platter all the way to the center, or at least towards the center. And this is the platter is moving at quite a high angular velocity in radians per second, or in terms of miles per hour, whatever you like to do. And the problem is that I've got a sector which I've marked in red here. In other words, it's a collection of bytes that I've actually written onto the platter, and it's revolving at high speed. And my task is to calculate the position of this sector when it next comes round, and calculate the way of actually placing the read head or the write head, depends whether you want to read or write, immediately above the sector that I need to read from or write to. So you've got two factors in this system: a moving disk and a moving read-write head. So let me say a few words about the disk structure. A fact of the matter is that disks do provide the bulk of computer memory, and modern disk drives are addressed as large one-dimensional arrays of logical blocks of storage. So what I'm talking about is logically, from a logical point of view, and in computer science, data can be addressed as an array, so moving from left to right along the array. And maybe the first byte, I've got a first byte and then the second byte and a third byte and a fourth byte. In other words, I can always arrange data in terms of, think of it in terms of an array, like I've got a first element, second element, third element, and so on. And each array consists of logical blocks of storage, which is capable of storing 512 bytes, 1024, 4096, and so on. I mean, 4096 seems to be a fairly common sector or logical block size. And this logical structure is mapped onto physical sectors of the disk in sequence. So, for example, sector 0 is going to be placed on the first track in the first sector of the outermost cylinder. And when you've used all that, you can take the next element of the array of data that you want to place onto the hard disk drive, and you continue in exactly the same way. I mean, perhaps you're looking at the um, nth element of the array that you now want to place on the disk. Well, you go to the second cylinder and place it in the first sector, and so on. So hopefully that's reasonably clear. Problem is, um, the problem is that in microelectronics and engineering, nothing's ever really perfect, and there's every possibility that a given disk does have defective sectors. In other words, there are sectors that you can't actually use. You can't read data from, you can't write data to, just because of imperfections of manufacturing process. Therefore, often the physical addresses of the sectors on the disk aren't known as a result of this. So the idea is that you can map, if you've got data and you conceptualize it in terms of a one-dimensional array, you put everything into an array, you can map each element of that array onto a physical sector on the hard disk. And as a result of that, let me just say, as a result of that, um, you need to associate each element of your uh, um, array of data, your logical array of data, with a physical address. And guess what? You can uniquely identify every point on the disk by means of a sector number and a particular byte. And you don't really need anything else. So it's a particular track and a particular sector on that track. I mean, that's going to be the physical address. Well, I've got a note about cylinder zones, and I'd like you to find out a little bit more about cylinder zones, what's meant by cylinder zone. The number of sectors within a track varies, of course. The further a track is from the centre, the greater its length, and therefore the greater the number of sectors it can contain. Obviously. I mean, that to me is obviously. So if you've got a track very close to the centre of the disk, maybe it's just got 1,000 or 2,000 sectors. On the other hand, maybe 1,000 or 2,000 sectors, yes, that's right. But as you move to the outside edge of the platter, I mean, maybe you've got 60,000 sectors, because the lengths of each concentric circle varies as you move from inner to outer track. And hopefully that's clear. So the number of sectors per track has seemed to be steadily increasing. I mean, maybe you just get 100 sectors per track on the outer zone. Many thousands of cylinders are common on a disk system, as I said earlier. And let's move on to the heart of what I'm here to talk about. as far as disk drives are concerning, so we're not talking about robotic devices, we're not talking about collision avoidance systems or anything else at the moment, but there are similarities and parallels between all those systems. So the access time of a hard disk drive has two main components. And I'm sure you're going to ask, quite naturally, what on earth is meant by an access time? I mean the time it takes to either read data from the hard disk drive or to write data to the hard disk drive. That's accessing that's using the hard disk drive for its fundamental purpose of storing data. So the first element is the seek time. So that might sound a bit strange, but it is simply the time for the disk arm to move the head or heads to the cylinder containing the target sector that contains the sector you want to read or write to. So the seek time. How long does it take the arm to move to where the desired sector is? Okay? And the second element is what's called rotational latency. And latency just means delay for our purposes. It's the additional time that the disk drive, needs to wait for the disk to rotate the desired sector to where you parked the head. Okay, so two elements: seek time, rotational latency. And again, I go back to something I asked you right at the beginning of this lesson, and it's could you try and find out how long it takes a disk arm to move one track from one track to another, to a track A to track B, where B is the next track? How long? It's going to be a very, very, very small amount of time, but what is it? What is it? And again, a rotational latency. I mean, in the worst case, maybe you've got to, once you've parked the head, in the worst case, you've got to wait for the time it takes for the sector, which you've just missed. It's just whizzed past, fraction of a second too late. It's whizzed past. How long does it take that sector to revolve 360 degrees round the disk? So it's now under the disk head. How long? Well, it depends on how fast, doesn't it? How fast the disk is travelling. And the obvious question is, does the disk does it travel at uniform speed, or is there any kind of variation in the speed in which it travels? Right. Next is a definition of disk bandwidth. So here we go. A disk bandwidth is the total number of bytes transferred, right, divided by the total time between the time that you request either data to be read or data to be written and the completion of that task. So in other words, it's like intuitively, it's the amount of data that can be transferred either by reading or writing. How long is it going to take? What can the disk drive system accomplish? So the access time and the bandwidth can be, guess what, improved by appropriate scheduling of disk requests. Okay, why? What do you mean? You might be asking. Well, let's begin at the beginning and think about using a disk. A computer may be using a disk to, all its programs need to store data safely or get data from the disk on which it's stored. When a program or a thread or a process or requests any input or I/O, which I've written I/O, when it requests any input or output, it issues a system call to the operating system, like Windows 10. Tell Windows 10 you want to read all the data on the hard disk drive that relates to the particular image of interest. You've stored an image on the hard disk drive. So the logically, and it's a purely logical question, the request specifies, first of all, well, what do you want to do? Is it input or is it output? One or the other. Can't be both, can't be neither. What do you want to use the disk system for? You want to do input or do you want to do output? And secondly, specify your disk address. And in other words, you will remember that a disk address is a physical address, and it's going to be determined by the sector number, maybe the cylinder number, and the offset from the beginning of the track, or something along those lines. You need to specify which sector the data is to be read from or written to. And reading and writing are inverse operations. Thirdly, you need to specify a memory address. And this is obvious because you've got some data somewhere that you want written to the disk. Well, you've got to tell the computer where it's being stored, like a particular memory. What's the memory what's the memory address of the data that you want to be written to the hard disk? And likewise, if you're reading data from the hard disk, the computer needs to know, well, okay, I can fetch it for you, I can get the data for, but where do you want me to put it? So in other words, again, you need to specify perhaps a memory address. I mean, it might be you want the data sending to your screen, because perhaps what the data you've gotten is that of an image, and you want to display the image. So, secondly, if the drive or the controller for the hard disk drive is busy, as it's likely to be for most of the time, all the requests will have to be queued. And another name for queuing here is buffering it. So perhaps you've never heard of the word buffer. And it's going to be queued on what's called appending queue. It's a queue of requests that are pending execution or activation. So in real context, a multi-threaded system, for example, because in a computer, whether or not you know it at this point in time, there's maybe just one CPU, one processor in your computer, but it's handling the execution of possibly hundreds or even thousands of different threads, lots of different programs. I mean, maybe you're playing music that you've just received from the internet, and you're displaying not only one video in one logical window on your screen, but you're playing a second video in a second logical window at the same time that you're actually typing data into the computer. I mean, maybe you've actually got a third window which contains a Word document, and you're busy doing that. Okay, so you can think of there being a queue of pending requests at any given time, and more requests are likely to join this queue at any particular time. So here is the core of our talk, schedules. I want to think of an applicable schedule to the requests, a list of requests for reading and writing the hard disk. And I'm imagining that I've got this list from left to right that have arrived in that order. In other words, the first request, which is to read data uh, from track 100 and then read data from track 200 and then write some data on track 50, write some data here, maybe read some data here, write and read. Doesn't really matter. Right. Supposing I've got a list of requests, I'm asking the hard disk system to perform all these actions on my behalf. Right. And I'm going to assume that the read or write head is in the vicinity of, I guess, sector 40. Somewhere on track 40. So that's a bit unclear. Block 40 I'll put here. On cylinder 40. I'm assuming that the head is in the vicinity of track number 40. Okay, so hopefully this is clear, right? What I mean by an input or output request, and hopefully it's clear what I mean by a list and why successive requests do appear. And maybe this request is to write data to part of track 100 in order to save my Word file. Here I want to read data. So I'm writing here. I want to read data here because I want to display an image. And maybe I want to, or the operating system wants to save data on track 50 because it's some important internet information that's just arrived from the White House. All right. So the first schedule. Whoops. Let me just go reset that. The first schedule. Oh, where have I gone? No. The first schedule is called first come, first served. All right. It's like a queue to get on a bus. First in the queue is going to get on the bus first. First on this queue is the first request that's going to be dealt with by the system. This is going to be the second because it was second to arrive. This was a second request. This is the third request, fourth request, and so on. First come, first served. So it's in some sense it's obviously fair, but I mean, I got my request in before you, and it's going to be serviced before your request. In some sense, it's fair, but it doesn't provide the fastest turnaround of servicing the requests in general. It doesn't minimize the time you and I have to wait to have a request serviced. So anyway, if the read-write head is at cylinder number 40 initially, the following chart will actually indicate the operation of the first come, first served algorithm. So here we go. And what I've done here is to specify the original list of requests from left to right. So remember, 100 was the first request, 200 was the second request, and the horizontal line here indicates cylinder number, and the red asterisk represents the position with respect to a particular cylinder. So here, the read, sorry, it represents the position of the read write head. So here, the read write head is at cylinder 40, and the first request, as you can see, is to move to cylinder 100. And that necessitates moving the read-write head from cylinder number 40 all the way to cylinder 100. Then the second request is, look, read or write data from sector 200, somewhere on sector 200. Do it. So the read-write has to move from cylinder 100 all the way to cylinder 200. And the third request is to do something with cylinder number 50. So here we go. We have to travel from cylinder 200 all the way to cylinder 50. And then next I have to travel to cylinder 125, then back to 55, then 60 and so on. So think of this as a map of the position of the read-write head. First it's 40, then 100, then 200, then 80, then 150. Sorry, 125 I think that is, or something. And so on and so on. And one thing that you might have already done mentally is to say, well, can we actually measure the distance of the journey that the read-write head takes? And you might have come up with a particular answer to that question. And it's easy to calculate. It's 100 minus 40, which is 60, plus 200 minus 100, so that's 160, and then you've got this length, so it's 200 minus 50, so another 150 sectors it has to cross, and so on. So notice that we can actually calculate the total head movement in the following way. And as I said, I'm just following the calculation as I've described it. 100 minus 40 plus 200 minus 100 plus 200 minus 50, etc., etc., etc. And I reckon that the sum is of the order of 670 tracks that the reading writing head has to cross. And this figure is a measure of the total seek time latency. But you can think of this as simply the distance the read-write head has had to travel. So you might think, well, that's okay, that's very clear, but is there anything we can do to improve the journey time? I mean, after all, if you are given a list of 100 different companies which want goods delivered to in central London, you would probably plan delivery in terms of finding the nearest place that you've got to deliver an item to, and then the next nearest, and then the next nearest after that, to try and minimise and make your total journey time efficient. And the idea here is that if the request for travelling to track number 20 and 50 could be serviced together before going to track 200, or maybe after going to track 200, the total head movement could be decreased significantly. Okay, so what I've got here is the original chart documenting the the journey of the read-write head, and it looks like that. There's zigzagging, there's wild crisscrossing of uh, the hard disk platter. The idea here is, well, uh, this is where the disk read-write head is. Wouldn't it be an idea perhaps to go here, then go here, because after all, travelling from 50, it's 40 to 20 involves a journey of 20, crossing 20 uh, tracks, and then visit and deal with this request, which involves crossing to track 50, which involves a journey of 30, and then maybe go to this, it involves a journey of 70. Maybe, I don't know, maybe look at this, and then finally deal with this. And what I have in mind here is what's called the shortest seek time first. So it's not first come, first served, it's shortest seek time first. And what this actually means is, well, your schedule should uh, demand that the uh, the track nearest to where the read-write head is visited first. Which of the requests in the list is the next? The next task to be done is to service the track that's nearest to you, where the read-write head is. So it's a reasonable assumption. Best to service all requests close to the current head position before moving the head to a remote location. So SSTF selects the request with the minimum seek time. And remember what seek time is. It's the time it takes to get from track A to track B from the current head position. And the above strategy would involve rewriting the list of requests into this list here, and check to make sure that after the read-write head has gone to track 50, which is the nearest track to track 40, then visit track number 55, which is the nearest track that needs to be serviced of all the requests that have come in. We get the following chart, and check all this. Visit 40, visit 50, visit 55, visit 60, visit 20, visit 100, visit 125, and then finally visit 200. And this compares to the shape of the journey generated by first come, first served algorithm. So think about that. I think I got this wrong in discussing it. Right? 40 then 50, not 40 and then 20. Right? 40 then 50, difference of 10. 40 to 20 would have involved crossing 20 tracks. Okay, so just check that. Make sure you get what I've got in this diagram. So that's the new list of requests that have come in and have been reordered according to the shortest seek time first scheduling. So note that in SSTF there are no major swings from one end of the disk to the other. This means that avoidable journeys across the disk are in fact avoided. And as a partial explanation of what I've just said, you can calculate the sector seek time, which is something of the order of 10 plus 5 plus 5 plus 40, etc., etc., which is 240. Check it. Check that. Represents the actual journey taken by the read-write head. Check it. All right. So this algorithm is a form of the shortest job first algorithm, and like the shortest job first algorithm, it may in fact create starvation conditions, and you need to think about why that does. And by starvation I mean that a request will never be dealt with, will never be serviced. And the hint is that, well, what happens if the read-write head is in somewhere near sector n, and more requests come in which are close to sector n, or maybe the request that's waiting to be serviced at sector 200 will never get a look in, will never be dealt with. So finally, I just want to mention the elevator or the lift scheduling algorithm, which is called SCAN. And in this scheduling algorithm, the disk arm traverses the platter first in one direction and then the other. And it serves requests as it does this traversal. So if I'm moving from the left part of the disk to the right part of the disk, then maybe if a new request appears just in front of the read-write head, it will be serviced very, very, very quickly indeed. On the other hand, if I've just moved from track number B and a request comes in behind track B, then it's going to have to wait quite a long time to be serviced. So in order to understand how it's operating, you need to know in which direction the arm is moving. So quick explanation is, if the head is moving towards the left edge of a disk, it will do 20. Then on reversing direction it will do 50 and 55, etc. So just to repeat myself a little bit, if a request comes in just in front of the head, it will be serviced almost immediately. If behind the head, it will have to wait for the reverse sweep. So finally, suppose there is a uniform distribution of requests for cylinders. Consider the density of requests when the head reaches an extremal position and reverses direction. You can think of it in terms of a lift built onto the outside of a hotel which has 100 floors, and you're descending from floor 100, and you're dealing with all requests for the lift on the downward journey. And when you get to the bottom, let's think about the situation. The chances are that there are going to be far more requests pending at the top of the building than there are at the bottom of the building. And the reason being is that you've just arrived at the bottom of the building, and therefore you have serviced all requests that have been present close to the bottom of the building. So it makes sense to jump, on reaching one side of the disk, it makes sense to jump to the other side of the disk when you reach the other, because there is a probability of there being a lot more requests there. There will be relatively few requests in front of the head. Greatest density is the other end of the disk. These waited the longest, so why not go straight to that locale? And the latter is the idea behind this algorithm. It's a variation of the scan algorithm. When the head has traversed the platter, it immediately returns to the extremal position without working on requests during the return trip. So finally, do have a look at this video clip, the video that was shown to you in the first part of this topic. Have a look at it, and in addition have a look at this video, which gives a bit more technical detail. about hard disk drives. And what we need to consider is the development of solid state devices and how they beat the pants off hard disk drives in terms of access speeds and so on, and the ways in which the two kinds of disk drive differ. Finally, two questions for you to answer, as I've already suggested at the beginning of this talk, is how fast do hard disk drives rotate, and how fast, in fact, does a head move? And I've suggested that the speed of a hard disk drive in terms of its angular velocity is enormous, and the speed at which a head moves across the disk is very fast. In other words, it takes next to no time at all to move from one track to another. But the question is, how much time does it take to move, say, across 10 tracks? Okay, so tell me next week. Thank you very much.